like, subscribe, and comment. We really appreciate knowing what's resonating with you, and don't be afraid to make suggestions for future episodes. Hey, welcome to the November 2025 The Automation Loop Reaction Series, where we are currently exploring AI and how it works. I'm Tim.
And I'm Tim. Last month, Tim, we watched part of a video that explored and explained embeddings, the mappings of words to numbers. This month, we're going to continue in that same video as it appears it is going to build further on that concept. I can't wait to see where this goes.
Yeah, same here. Let's get into it.
All right. All right, Tim, are you ready?
Let's do it.
Roll.
In the case of transformers, you really want to think of the vectors.
Okay, so actually, let me just set this up a bit. Last time we left off with what are embeddings, and we saw how embeddings work into the parameters of an AI model. We left with this screen right here, right about here. So we are just going to continue on the next chapter, and here we go.
In the case of transformers, you really want to think of the vectors in this embedding space as not merely representing individual words. For one thing, they also encode information about the position of that word, which we'll talk about later. But more importantly, you should think of them as having the capacity to soak in context. A vector that started its life as the embedding of the word king, for example, might progressively get tugged and pulled by various blocks in this network, so that by the end it points in a much more specific and nuanced direction that somehow encodes that it was a king who lived in Scotland.
So, Tim, early on in one of our videos, we saw how when we first saw embeddings, I think in general, it was in the context of the words, the language is changed into numbers. And then at one point we saw, hey, the numbers adapt to their context around them. And it looks like that's exactly what this is describing, where we saw the embeddings get pulled for the column words. And now, based on the context of the other embeddings, each embedding is being kind of pulled and influenced by the embeddings around it.
Yeah, it's in my very basic understanding of this, it strikes me as it's essentially taking black and white television and sort of adding color, like adding more metadata, more value to the information being conveyed, the context of the information.
That's right. Yeah. So it looks like, let's roll.
Who had achieved his post after murdering the previous king, and who's being described in Shakespearean language. Think about your own understanding of a given word. The meaning of that word is clearly informed by the surroundings, and sometimes this includes context from a long distance away. So in putting together a model that has the ability to predict what word comes next, the goal is to somehow empower it to incorporate context efficiently. To be clear, in that very first step, when you create the array of vectors based on the input text,
what we're trying to do here is really get the model to be able to behave a bit like we do. It's essentially reading comprehension, like that most of us learned in kindergarten and elementary school, where we learned this process of how do you read something and be able to understand the words that you read in the context of what you read. I think that's really the idea here. We're trying to get the AI to be able to do the same thing.
Yeah, reading comprehension. Yeah, that's absolutely right.
Each one of those is simply plucked out of the embedding matrix. So initially, each one can only encode the meaning of a single word without any input from its surroundings. But you should think of the primary goal of this network that it flows through as being to enable each one of those vectors to soak up a meaning that's much more rich and specific than what mere individual words could represent. The network can only process a fixed number of vectors at a time, known as
to talk about this matrix, and even though it's not what we think of as a network in the traditional sense, it's obviously a software-defined network that's happening in the memory space of the train. I actually don't know what this machine is called that does this training. It's a software platform. It's a what's this thing?
I think you've identified our next topic for our next video, perhaps. Yeah, I don't know. I don't know what this looks like. Is it happening in one server, or is it maybe more likely happening across multiple servers connected by a very fast network?
It's definitely got to be multiple servers for sure, right? This isn't
Yeah.
happening on a single server, but interesting use of the word network specifically, the way he talks about this, in this case, this context.
Yeah. Let's see how this plays out. This is getting really interesting.
Its context size. For GPT-3, it was trained with a context size of 2048, so the data flowing through the network always looks like this array of 2048 columns, each of which has 12,000 dimensions. This context
2048 columns times 12,000 plus dimensions. I don't know if that's I don't know if that's a lot of data or not a lot of data.
I have no way to
I don't
measure.
know.
Yeah. Yeah.
This big.
And how did they pick these numbers? Like, why 12,228? I'm so curious.
Yeah. I think that was the 12,228, that was the number of dimensions. Remember, for a given word or for a given
yes.
word, you can
Yeah.
measure it in 12,000 plus dimensions. At least this model could.
Yep.
Oof.
size limits.
We're just trying to solve a 12,000 dimensional problem, Tim. Come on, keep up. You got this.
How much text the transformer can incorporate when it's making a prediction of the next word. This is why long conversations with certain chatbots, like the early versions of ChatGPT, often gave the feeling of the bot
This
kind of
finally
losing
makes
the
sense.
thread of conversation
Right?
as you continued too long.
It can only have this much context at any given point in time. It's like a sliding context, right? So it's constantly forgetting stuff because it only has so much buffer, essentially.
Yeah, and as this was being described, my thought went to the system prompts you give the large language models. A system prompt is something in the background where you say, "Hey, LLM, you are a friendly assistant, or you are a wizard, or you are something," and it's my understanding that in those prompts, some of these companies, like who might have a companion AI or a character AI, say, "Okay, don't talk with users about, this, or this. And if they bring up self-harm, do this." I think that's part of the system prompt. And recently, Tim, what they saw is the longer a conversation goes on with one of these AI bots, the weaker that initial prompt gets. And I'm wondering if it's because it's losing context.
It's
So
getting
no,
diluted, essentially.
it's
Yeah.
getting
Yep.
diluted. Yeah. So if the longer you talk with a chatbot, the less the initial system prompt, I think, matters. That's what I'm
Yeah.
gathering from this based on some other
Yep.
contexts I've seen.
And I think it's
And
really important to understand this idea because we're so used to the way that we work and the way that our brains function and the way that we interact with other humans. And because AI responds to us in very human-like terminology, we tend to think that it has human capabilities, and it does not. And we need to be aware of that when we use the tool, that like these kinds of things happen, that it has limited context, that it is going to forget, it isn't going to behave like a human does.
yeah, and then it just kind of smoothly reacts there like, "Oh, thanks for reminding me about that. Yeah, you did say that."
Right.
It has no idea. It's just going with what you said.
Yeah,
It looks
exactly.
like, at least.
Right. You could
Wow.
probably say, "Don't you remember when we talked about those pink pigs in flamingos?" And they'd be like, "Oh, sure."
Oh, yeah, totally. You know what? I'm going to try that at some point. Okay.
We'll go into the details of attention in due time, but skipping ahead, I want to talk for a minute about what happens at the very end. Remember, the desired output is a probability distribution over all tokens that might come next. For example, if the very last word is professor, and the context includes words like Harry Potter, and immediately preceding we see least favorite teacher, and also if you give me some leeway by letting me pretend that tokens simply look like full words, then a well-trained network that had built up knowledge of Harry Potter would presumably assign a high number to the word Snape. This involves two different steps. The first one is to use another matrix that maps the very last vector in that context to a list of 50,000 values, one for each token in the vocabulary. Then there's a function that normalizes this into a probability distribution. It's called softmax, and we'll talk more about it in just a second. But before that, it might seem a little bit weird to only use this last embedding to make a prediction, when after all, in that last step, there are thousands of other vectors in the layer just sitting there with their own context-rich meanings. This has to do with the fact that in the training process, it turns out to be much more efficient if you use each one of those vectors in the final layer to simultaneously make a prediction for what would come immediately after it. There's a lot more to be said about training later on, but I just want to call that out right now. This matrix is called the unembedding matrix, and we give it the label WU.
So that
Tim, I'm
sounds
just
like
gonna,
our next topic. And
yeah,
go ahead.
I'm gonna sit here and look confused because what just happened? I was following and then I just fell off
And
the
then
train
this, I
tracks.
feel like this happens every time, which is where I think like, oh, I'm beginning to understand this. And then, nope, I'm definitely not.
What
And I
was
don't
he?
even,
Yeah, go ahead.
I don't know that I even know how to react because I don't really understand what just happened.
So yeah, he was focused on the last word. Yeah, I have a lot of questions about this. For example, is every word by last word, does he mean the most recent word? Does every word go through this, or only the last word in the sentence? Uh, that's what I'm trying to process
Yeah,
here.
because then he said we only look at the last one, but then actually we look at them all simultaneously and then we unembed them.
But only the last word.
So I'm
I
not sure why
think.
we ever embedded it if we were going to just unembed it. There must be a reason.
Yeah, I'm just going to sit here and look puzzled for a moment, if you'll allow me. Okay,
Yeah.
thank you.
And so I think what we've learned is that the more you know, the more you realize you know less
Yep, you know less. Wow,
than you thought you did.
I don't know. I think this chapter's wrapping up. So let's just see how this ends. Maybe he'll pull it all together for us.
Again, like all the weight matrices we see, its entries begin at random, but they are learned during the training process. Keeping score on our total parameter count, this unembedding matrix has one row for each word in the vocabulary, and each row has the same number of elements as the embedding dimension. It's very similar to the embedding matrix, just with the order swapped, so it adds another 617 million parameters to the network, meaning our count so far is a little over a billion. A small, but not wholly insignificant fraction of the 175 billion that we'll end up with in total.
I'm going to back up there real quick to that
But not wholly insignificant fraction.
to that shot. So between the embeddings and unembeddings, and I kind of understand that now. Yeah. We have a billion. What did he call them? We have a billion of these things. Weights. We have a billion weights, and the total weights for this model he's looking at for GPT-3 is 175 billion.
Billion.
So there is just a ton
We
more.
we barely touched the surface.
Oof. Geez. Okay. Let's see if he wraps this up here.
Of the 175 billion that we'll end up with in total. As the very last mini lesson for this chapter, I want to talk more about the softmax function, since it makes another appearance for us once we dive into the attention blocks. The idea is that if you want a sequence of numbers to act as a probability distribution, say a distribution over all possible next words, then each value has to be between 0 and 1, and you also need all of them to add up to 1. However, if you're playing the deep learning game, where everything you do looks like matrix vector multiplication, the outputs that you get by default don't abide by this at all. The values are often negative or much bigger than 1, and they almost certainly don't add up to 1. Softmax is the standard way to turn an arbitrary list of numbers into a valid distribution in such a way that the largest values end up closest to 1, and the smaller values end up very close to 0. That's all you really need to know. But if you're curious, the way that it works is to first raise e.
That was the part I understood out of like maybe all this. Okay.
At least here, there's some what seems like relatively basic math concept that, like, oh, okay, I can wrap my head around that.
Yeah, yeah. I wonder if that's a good place to wrap it up for this
I
one. Maybe
appreciate
next one.
his I appreciate his explanation of, well, that's really all you need to know.
Yeah,
Let's just leave it at
that's
that.
perfect place to stop for right now. Tim, I found that a bit overwhelming.
I also enjoy the fact that he references what we just went through as a mini lesson, and you and I are both here like mind blown. And he's like, "Yeah, really, that's just kind of like the morning. It's just, it's really nothing."
Yeah, there is so much here. There is so much here.
So, Tim, what'd you think of the video? I don't know, like, wow, like he said it was just a little mini lesson, but to me that was like a mind blown situation.
Tim, I was with him. Uh, I was with him for the part where we saw in a prior video about how the column words tokens get made into numbers, and then those numbers get influenced by the context of the other numbers around it, which represent the meanings. I was with him for that, and then I fell off a wagon, or however wagons are. I don't know how wagons work, I guess, but I fell off of it. I'm not on it anymore. When it came to unembeddings, it didn't make sense.
Yeah, I was following and then I wasn't following and then actually I was kind of following again at the end. And I feel like my main takeaway from this was just really better understanding some of the technical ways in which language models and AI is trained and the way it's created helps me better understand its limitations. Because I've always found like I get very frustrated when I'm working with the AI model and it does something where it's like, wait, just 2 seconds ago I told you not to do that, and it goes and does it anyway. Now I better understand because of that sliding context that it forgets stuff, and so like that's just part of working with a language and a model and AI. Like you just have to adjust to that.
And that's an important point. And I think it wraps back into, if you are a leader being expected to implement AI, you need to have the right staff around you to advise you properly,
Yeah.
because it's just every time we look at these things, we hear explicitly or non explicitly non-determinism. It's non-deterministic.
Yes.
And at scale, non-deterministic behavior is like terrifying. It's still terrifying to me.
Yeah. So yeah, as we look at the ways in which we might begin to use AI in our networks and in management of them, still very concerned as far as the ideas behind them and the fact that they are so non-deterministic, as you said.
Yeah, absolutely. Well, maybe the next video we'll just continue on with this video and see how this gentleman wraps it up for us. Maybe I can
Continuing down the rabbit hole.
get back on that wagon. Yeah, and continue the journey.
Well, that wraps up yet another one of the reaction series episodes here with Tim and I. Hope you enjoyed this and learned something as we did here on this episode.
Yep, folks. As always, like and subscribe, leave comments, and always stay curious.